While missions like NASA's Lunar Reconnaissance Orbiter have provided detailed maps of the entire lunar surface, U-22 has yielded information about the subsurface structure of the moon's far side, and details about the lunar regolith that you can only learn by physically stirring up the dirt. The results could help guide further lunar exploration by both China and the US. U-22 made 3 critical discoveries by playing in the lunar dirt, all of which could have implications for future robotic and human exploration of the far side of the moon and our satellite's southern polar region. In the first 25 lunar days, around 738 Earth days, of U-22's mission, the rover crawled over more than 2,700 feet across the 110-mile diameter von Karman impact crater within the Aitken Basin at the moon's southern polar region. The U-22 rover found the terrain to be relatively flat and free of rocks compared with areas on the side of the moon facing Earth, such as the Mare Imbrium explored by the first U-2 rover from 2013 to 2015, and by Luna 17 and Apollo 15 in the early 1970s. Rocks along the traverse route are relatively rare in comparison with those scattered around the U-2-1 landing site, the story authors write. Larger rocks like those seen at Mare Imbrium are absent from observations. At least we now know what the small boulder responsible for the Mystery Hut mirage, now dubbed Jade Rabbit, stood out so well at the rim of a crater. And speaking of craters, there are 88 impact craters within 50 meters of the path U-22 has taken across the moon, with an average diameter of almost 12 meters. The vast majority come in at less than 10 meters diameters. Planetary scientists believe the craters to be largely secondary impact craters from ejecta thrown from the impact that created the Xinyu crater west of the rover's landing site. It was in the bottom of a 2-meter diameter crater that U-22 discovered another compelling mystery, a dark greenish glistening material originally described as gel-like, which may be rock melted together by the heat of an impact. By observing how lunar regolith stuck to the U-22 rover's wire mesh wheels and measuring how the wheels occasionally slipped in the regolith, the researchers were able to calculate its consistency and load-bearing properties. The regolith resembles dry sand and sandy loam on Earth, they write, demonstrating greater bearing strength than that identified during the Apollo missions. The somewhat sticky property of the lunar regolith was observed across multiple lunar days, suggesting it is a regional characteristic rather than a site-specific property of a patch of regolith, the researchers write, and they theorize the property may result from greater and more prolonged exposure to space weathering than lunar near-side regions. How they did it. The U-22 rover is a relatively lightweight, 77 pounds, 6-wheeled semi-autonomous rover equipped with a panoramic camera, near-infrared spectrometer, and ground-penetrating radar, among other scientific instruments. The rover landed on the moon on January 3, 2019, as a component of the Chang'e 4 mission, the first soft landing on the far side of the moon. Together, the Chang'e 4 lander and U-22 rover are the successors to the Chang'e 2 lander and original U-2 rover mission, which made the first soft landing in the Mare Imbrium on the moon since Luna 24 in 1976. What's important about the U-22 findings? The U-22 rover findings could help guide the design of future robotic missions to the southern polar region on the far side of the moon. The more supportive than expected soil could support larger-scale robots, the researchers note, while the cratered surface could necessitate legged robots, hybrid wheel-legged robots, or tethered rovers for future exploration. U-22 wasn't able to get up close and personal with the greenish gel-like substance because researchers feared it wouldn't be able to climb back out of the crater. And given that the sticky regolith adhered to the lugs on U-22's wheels rather than the wire mesh, future missions might consider coating the lug's surface with a special anti-adhesion material. Both the China National Space Administration and NASA plan to explore the moon's southern polar, China as part of the International Lunar Research Station program it is pursuing with Russia, and NASA as part of the Artemis program and its Commercial Lunar Payload Services initiative. U-22 will continue exploring the far side of the moon, and the researchers hope to make better use of the tools the rover makes available to learn even more about the environment. And they're not just considering the dedicated science instruments. For instance, they write, trenching experiments can be conducted using one of the rover's wheels to expose the near subsurface soil. Far side of the moon remains poorly known. Lunar farside exploration is challenging because maneuvering rovers with efficient locomotion in harsh extraterrestrial environment is necessary to explore geological characteristics of scientific interest. During its journey, U-22 has experienced varying degrees of mild slip and skid, indicating that the terrain is relatively flat at large scales, but scattered with local gentle slopes. Cloddy soil sticking on its wheels implies a greater cohesion of the lunar soil than encountered at other lunar landing sites. Further identification results indicate that the regolith resembles dry sand and sandy loam on Earth. In sharp contrast to the sparsity of rocks along the traverse route, small fresh craters with unilateral moldable ejecta are abundant, and some of them contain high reflectance materials at the bottom, suggestive of secondary impact events. These findings hint at notable differences in the surface geology between the lunar far side and near side. Experience gained with U-22 improves the understanding of the far side of the Moon, which, in return, may lead to locomotion with improved efficiency and larger range. Planetary exploration using orbiters or rovers has continued to extend the boundaries of science and technology in the last few decades. The Moon, the closest celestial body to Earth with potentially exploitable chemical and mineralogical resources, is one of the most substantial destinations of exploration missions. The lunar exploration effort peaked after the successful Apollo program. Since then, there have been 20 successful landers on the near side of the Moon as a result of crewed and rover-based missions. However, no astronauts or landers arrived on the lunar far side until 2019, mainly due to the blindness of the side with respect to communication and monitoring, although evidence collected through remote sensing had indicated the distinction of the two sides in gravitational field and material composition, providing a strong impetus for in situ exploration of the far side. The QUEQIAO relay satellite, which is the first relay communication satellite outside Earth's orbit, and features the largest satellite umbrella antenna diameter, 4.2 m, acts as a high-speed bridge to transmit data and commands between the ground station and U-22, with a time delay of 1 to 2 s in one-way transmission. Primarily, U-22 was directly controlled by uploaded commands generated from ground teleoperation. However, it can also work in autonomous mode on relatively flat terrains. Research details. Benefiting from U-22's locomotive venture consisting of a series of careful movements, in situ investigations of lunar rocks, soil, impact craters, and energetic neutral atoms emitted from the lunar surface have been carried out on the far side of the Moon. During this 2-year venture, one of the most exciting explorations involved the rover taking a risk of instability at the rim of a 2M crater on the 8th lunar day, owing to the detection of an unexpected gel-like material of high reflectance discovered at the crater's base. The dark greenish, glistening material viewed by PanCam at the closest safe distance from the crater after 2 painstaking approach attempts showed its distinctive shape, color, and texture from the surrounding regolith blocks. The material's appearance, which resembles lunar samples 15466 and 70019, obtained by the Apollo 15 and 17 missions, suggests that it could be an impact melt breccia, or a glass-coated agglutinitic regolith breccia, with a possible complex formation of impact-generated welding, cementing, and agglutination of lunar regolith and breccia. An inspection of the gel-like material, and even entering the crater to conduct close-focused investigation using payloads, would be of great scientific interest. However, because of the high probability of locomotor failures, the rover has been advised to limit any further movement. If U-22 drove down along the steep crater wall, it might be out of control due to the skid failure of the wheels. Furthermore, even if it enters the crater successfully, the rover will find maneuvering out of the crater highly difficult. Climbing attempts with severe wheel slippage is prone to cause large wheel sinkage, or even rover immobilization, similar to what was experienced by Spirit and Opportunity, especially when traversing on soft and deformable terrain. The interesting soil cohesion phenomenon is analyzed to be regional with multi-day observations. Intensive study of the chemical composition and physical properties of the lunar regolith is necessary to be carried out for further analysis. More notable findings are expected to be discovered by taking full advantage of the rover's capability. On the basis of in-depth understanding of the lunar far side, more powerful locomotion, higher intelligence, and advanced scientific payloads are needed for future lunar exploration with space robots in larger scales and harsher environments. If you enjoyed this video, please like it and subscribe to the channel. And don't forget to watch the other videos we made for you. Thank you.